All right, multivariable calculus, Math 150, Section 1, Lecture 4, test of the new system. So far, things look well, but we will know more in about 50 minutes. All right, so today we're going to do equations of lines. This is something you should hopefully remember from your old days, many, many years ago in Algebra 1. One of the reasons we like to do equations of lines is the big idea in calculus is locally any nice function looks like a line. So since everything looks like a line, you need to really understand lines. So how many different ways do you remember to write the equations of lines from all those years ago? Trying to see if I get all the lights on. There we go. So how many equations of lines do you remember? What are the different types of equations of lines?
Point slope.
So one is point slope. What's really nice about these names is they tell you the inputs you need. You need a point, say x naught, y naught, and a slope, m. And then the equation of the line is y minus y naught equals m x minus x naught. And if you think about what a line is once I give you a point and I give you the direction I'm going, the line is completely determined. And then any other point x, y, if you look at y minus y naught over x minus x naught, that will give you m, that will give you the common slope. Later, we will recast this in terms of vectors, and we'll find ways to write down equations of lines in 3 and higher dimensions. Because a line could exist in 3 space. I could draw a line in 3 space here. Do you know how to write the equation of a line right now in 3 space? Before reading this section, did you know how to do that? No. So you'd only covered in school your equations of lines on planes, but you could, of course, have a line in a more general space. OK, so this is the point slope. What else is there? Slope intercept. And so here you're given a slope m, and almost always the intercept is b. Now, with slope intercept, the intercept is usually the y-intercept. Does every line have a y-intercept?
There's one that doesn't.
Which one?
Any vertical line.
Yes, it does. There's infinitely many. As long as it's not x equals 0, all those vertical lines will have no y-intercept. So you have to be a little bit careful. But so what we would have here is y typically equals mx plus b. And so if you take x equals 0, that's y equals b, and that's where the intercept is coming from. All right, there's one last one. Does anybody remember the last one? Yes? Point, point. Excellent. So I have a point x naught, y naught, and I have another point x1, y1. I never remember what the formula is for point, point directly. If I'm given point, point, what do you think I should do?
Find the slope.
Yeah, find the slope. These two immediately give us the slope is y1 minus y naught over x1 minus x naught. And now that I have that, now I can use point slope. Okay. So I'm noticing that, boy, this likes to move. Okay. I'll have to think about this a little bit. Okay. So now that we have these 3 equations, let's see how we might rewrite them in several variables. And so the question is, which one do you think is going to work best from a vector point of view?
Point slope.
So point slope. So we have to be worried a little bit about where might things be intercepting. It's not a proof, but we just saw here with point, point that the first thing we did with point, point was we went straight to point slope. So let's think about what point slope would look like in a vector setting. So generalizing point slope. All right, so this is moving way too much. And so I'm going to try doing the following. All right, so we will have a point now. Maybe I'll write my point P naught will be x naught, y naught, z naught. Could I have more than 3 variables? Could I have a 4-dimension or 5-dimension? So the question is, do I want to just write something in general? Do I want to write x1 through xn, or do I want to just write x, y, z? There's really not much of a difference. If you can do the three-dimensional case, there's no real obstruction going to n dimension. It's which notation you're going to find friendlier. This is where you get to vote. Would you rather see x1 through xn, or x0, y0, z0? Any preference? Seeing no overwhelming preference, since x0, y0, z0 is on the board, we'll do it that way. So we now have a point in 3 space. So here's the origin, 0. And here is the line to the point P0. So P0 is some point on my line. Now, what is a line in space? It's all points that are going off in a common direction. So any point in the line could be the base of the line. How many of you have done physics? Okay, good. I have some crappy chalk here. If I were to drop this crappy piece of chalk, I want to do it for a good one, what's going to happen? It's going to fall to the ground. And how do you calculate how fast it goes? What do you use?
The acceleration due to gravity.
So that's part of it. And what else do you need to use?
The air resistance.
Well, no. This is an idealized experiment.
Initial y.
Initial y. So you want to start off with the potential energy being converted to kinetic energy. What's kinetic energy? Yes.
1/2 mv squared.
1/2 mv squared if we're subrelativistic, which is fine here. I'm not going to be throwing this chalk really fast. How do you measure potential energy?
It's mgh, so if you have the mass of the child.
Okay, but so what's h?
The height from which it's dropped.
The height from which it's dropped. But you can often choose where do you want your baseline to be. It doesn't have to start off with potential energy mgh. Maybe, am I assuming maybe the floor is 0? Maybe it's starting off at height 0. Maybe that's where I'm going to, and then things are going to be becoming negative. Or maybe the ceiling is 0. What matters is the change in potential energy equals the change in kinetic energy. Energy is conserved classically. So I get to choose where I define 0 potential energy to be, just in case anybody really wants to see the chalk drop. Okay? It's very similar to a line. I can choose what do I want to be my base point on the line. Is there any natural base point? If the line goes through the origin, okay, then I could say there's a natural base point in that case. But otherwise, it seems like a lot of points would be equally good. So choose a point. So we chose some point P0 on the line, and now we have a vector v in 3 space. Maybe I'll call it v sub x, v sub y, v sub z. And then our line is going to be given as follows. So the equation of the line through P0 in the direction of v is given as follows. All right, it is L of t, so it's going to be a function, is going to be P0 plus t times v. So for any value of t, this is going to tell me where I am. What is the easiest value of t to study?
0.
0. And if we take t equals 0, we get back that L of 0 is P0. This is why I'm choosing to call this point P sub 0. It's where I am at time 0. Good, I'm at some point on the line. And then as time passes, I see that I'm going at that point P in the direction of V. So if I go 1 second later, I'm now at the point P0 plus V. If I go back half a second, I get P0 minus a half V. This is going to be a one-dimensional object. Okay. If there is time today, I'm going to show you an object that is neither 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional, 4-dimensional. It's a non-integral dimensional object. And you've actually seen something similar to this before, if you've looked really, really closely. But you always want to get a sense of what is the complexity of the object you're looking at. In 3-dimensional space, I need 3 coordinates in general to specify where I am. If I'm lying on a line, I should really only need 1 input to tell me where I am at any point on the line. So at time 0, I'm here. And all I need to know is how long have I flown to figure out where I am at some later point in time. Okay, so everybody comfortable with a line is a nice one-dimensional object. You give me some value t, I can figure out where I am. Does this reduce to what we've seen here? So let's see how we could rewrite this. So we've got y is equal to, let's see, how do we want to write this? So we have y naught plus m x minus x naught. So in some sense, this is where we started on the y side, and this is where we are later. But we want to write this in vector. Right? So this is not really being written as a vector equation. This is written as just one equation. So I want to have some initial point, p naught, and I want to have some later time. So my later time would be my point y. What we're really trying to do here is we're trying to say, look, everything's a function of just one variable, t. You give me a t, and that gives me an x, that gives me a y. So what I really want here is I want to view these as x of t and y of t. That's going to be my line L of t. You give me some time t, and it gives me both an x coordinate and a y coordinate. What I'm doing here is you give me an x, and I know what the y is. Well, if you think about it, if you're on a line, and it's in a two-dimensional plane, once you know the x coordinate, you know the y coordinate. Unless you're in this really degenerate situation where you're just going straight up. But in general, if you know the x coordinate, you know the y coordinate. What we're doing here is we're saying we're giving you a time, and from that time, you then deduce the x coordinate, you then deduce the y coordinate. So what direction do you think we would be moving in here? We need to figure out what's our initial point. The initial point shouldn't be too bad. What do you think the initial point is? So what should the initial point be in this set?
Why not?
Well, that's just a coordinate. I want a whole point.
Okay.
So you're halfway there.
Why not an x naught?
An x naught, right? It's just the point x naught, y naught. Right. Now we need to figure out the direction we move in. What do you think the direction we move in should be? So you got to think about what it means for the slope to be m. So what does it mean for the slope of the line to be m? What's the geometric interpretation?
Change in y over change in x.
Change in y over change in x. So if I tell you the slope is m, how would you write that as a vector?
1m.
1m. If I change x by 1, I change y by m. So that would correspond to a v of 1m. And I would get the equation then, L of t would be x naught y naught plus t 1m. Or x of t is x naught plus t, y of t is y naught plus tm. And if you think about it, all I'm really doing here is saying, let's just replace x with x naught plus t. This is doing that change of variable that you've been doing in calculus all the time. Let's localize things about the nice point. And so if I write x as x naught plus t, then I get y equals y naught plus mt. All right, I wrote tm, not really a big difference. And then my change in x is just going to be t. So we can recover what we've done before. We can write the line equation in a way we've seen before. Okay? So this is how you find equations of lines. You need a point, and you need a direction. What if I don't give you a direction? What would you need then?
Another point.
You would need another. So 2 points determine a line. There's a joke, in business or marketing, 1 point determines a line. Which way does the boss want things to go? Yeah, sure, sales are going up. You need 2 points to determine a line. How many points do you need to determine a parabola? 3. How many points do you need to determine a cubic?
4.
4. Think about it. Parabola is ax squared plus bx plus c. You've got 3 unknowns, a, b, c. You need 3 equations to get those. So if you have 3 points, you can deduce it. A line is y equals mx plus b. You have 2 unknowns. You need 2 points. And then you can go through and solve. And in fact, that's what we did. You can write all of our equations of lines in the form y equals mx plus b. You often want to do this if you want to regard y as a function of x. How many of you remembered with fondness those implicit differentiation problems? I don't see anybody jumping up for joy and saying, yeah, we're going to be doing those again. You always try to write things explicitly. I want to write y as a function of x. That's not always easy to do. It's unfortunately sometimes easier to have things bundled together and learn implicit differentiation. You might think of the equation of something moving on an ellipse or something where they're bundled together. What we're trying to do here is we're trying to highlight the fundamental variable. There's some time variable, and at every moment in time, I have an x coordinate. At every moment in time, I have a y coordinate. And you give me the time, and I get both. What we were doing initially was we were looking at the x coordinate, and from that we were deducing the y coordinate. Okay? So what we'll do now is we will do the equation of, what would happen if I can move it just a second? There you go. We will do the equation of a line in 3 space when now we only have 2 points. We do not have the initial direction. So I'm erasing point. Well, actually, I don't even have to erase point. I can leave the phrase point because that's what we're doing. So say we now have the point P naught is x1 to xn. I'll do it. I'll still do x naught, y naught, z naught. X naught, y naught, z naught. And I'll do the point P1 is x1, y1, z1. I can now find the vector as x1 minus x naught, y1 minus y naught, z1 minus z naught. And I could write the equation of the line now as L of t is P naught plus t times v. And that will be the equation of the line. So I taught for a year at the best of the Big Ten schools, at least in football. So anybody know what school that is? Please use the full title.
Is it Wisconsin and Madison?
No, it is not Wisconsin at Madison.
Oh, Ohio State.
Use the full title, please. It's not Ohio State.
The
Ohio State University, actually. Right? The Ohio State University. It's not a Ohio State University. It is the Ohio State University. I've been saying the equation of the line. Nobody's been jumping on me on that. Is there only one equation for a given line? No. I could have another equation of the line. So I could call, instead of L of t, maybe I could call it capital L of t. Could be P naught plus 44 TV. Will that generate the same line in space? Yes. What's the difference between the two lines? Geometrically, they're the same. They will fall on each other.
If we're looking at t as time, the bottom line is going faster.
Yeah. By what factor?
44.
By 44. So if you want, on this line, we're moving forward 44 times as fast as we would be moving on this one. When I'm looking at this vector v, could I use a unit vector in this direction? I could. And that would give me yet another way of getting an equation line. So sometimes we use a v hat for a unit vector in that direction. So I could say v hat would be the vector v divided by the length of V. And then I could write maybe some kind of like block L of T would be P naught plus T V hat. And that would be yet another way of writing down an equation of a line. So depending on what you want to do, sometimes one system is a little bit better than another. It might be convenient to have a unit vector V for your slope. Okay? But they're all equivalent. So now I can give you a whole variety of problems. I give you a point, I give you a direction, you find me the line. Or I give you 2 points, find the line. And I could give you the question, do two equations generate the same line? How would you tell if two equations generate the same line? So there's a couple of ways you can do. What's the first check? Yes?
The slope.
Yeah, the slope. So take 2 points on the first line, take 2 points on the second, and calculate the slope or calculate the direction. If the directions are different, can they be the same line? No. So when you're doing a lot of analyses, sometimes try to do a simple test first. If they're the same, well, they've got to be in the same direction. Let me check and see if they're in the same direction. The other thing is choose a point on one and see if it's on the other. If there's a point that one has that the other doesn't, clearly you're fine, and they're different lines. So you often, if you have an equation like this, take t equals 0, here's some point p naught. All right, but then I have to figure out maybe in my alternate way, is there some time that would give me that point? So that would be the other type of question I could give you. Any other questions on lines from your reading or examples that you want to see? Everybody's fine with the rest of the section? Okay, what I want to do now, if you're fine with this, is I want to talk about some stuff that you probably haven't seen before and try to show you a little bit where some of this goes. So I'll first do some of the artwork stuff. So these are temporary buildings. We don't have as high quality stuff here. Okay. So we will see if this works. So I am. So this is a cultural art question right now. Anybody recognize this? Yes.
Is that from Star Trek?
So you make me proud. My daughter actually said that as well, which made me very, very happy. It is quite close to the symbol on the insignia for the Enterprise. And because the old Enterprise was such a great ship, they eventually said, you know what, each ship should no longer have their own insignia. Everybody should use this. It's very close to that. For a while, it was actually displayed in North Adams Close there. It's from Saul DeWitt. And just general art with just straight lines and whatnot. So here is one of my favorite artists of all time, Thomas Eakins. And this is, I guess, shad fishing at Gloucester on the Delaware River, 1881. And the reason I like this and want to see this, and it's probably not going to be displayed too well because I'm using the weaker camera, is at the time he cheated, according to the current art world. The four people here, somebody found, I think, a few decades after Eakins' death, those four people in the same clothes in a photograph of people on a road in New Jersey. And people then looked at the canvas again, and they noticed that there were a few dots at strategic points around the people. And then what Eakins had done is he had taken a photograph of people and had projected the photograph on the canvas and put dots so that he would have the perspectives correct. And then rather than having to spend the time to make sure he got all the sizes of the people and everything correctly, he just used this as a time saver. And hid the fact that he did this. I believe he told some of his students and protégés about this method, and they did this in their work. And once people noticed this, they then went back and they looked at a lot of other works of Thomas Eakins and saw that he had done this in other places as well. But it had not been noticed for a long time. If you think about it, it's basically just the equation of a line. You've got some object that you're projecting, you've got a light source, and you look at where the light hits. The second thing I want to show you, which is related to cheating, anybody know what movie this is? Yeah, I mean, it says so up there. I don't know if you, how many of you actually saw the movie Tron? So it was actually a commercial failure when it came out, but it was revolutionary in terms of special effects. So this is at the dawn of what computers can do. What do you notice about the special effects, for the most part? Yes?
They're all like straight lines.
They're basically straight lines. Every now and then you've got some curves, but for the most part, the special effects are straight lines. And it was a monumental achievement doing the special effects like this. They were not eligible for Academy Awards for special effects because it was felt that they were cheating to use computers. Whereas when you watch movies nowadays, it's not clear anymore nowadays, what's actually in the movie and what's been digitally added. So what I want to do now is talk a little bit about, okay, we've got about 25 minutes left, good. I want to talk a little bit about what we mean by dimension, and I want to give an application to calculus which you may have seen. So mostly, when we think of dimension, we think of something as 0 dimension, 1 dimension, 2 dimension, something like that. But there could be other dimensions. And this goes back to one of the themes from the class, that it is important to have a rigorous understanding of what's going on. It's very easy to do things that look right, but are subtly wrong. Also, I want to show you where the math goes. So if you continue with math or other things like this, what might you see? So let's start off with the segment 0, 1. And we're going to construct something that's called the Cantor set. How many of you have heard of the Cantor set? The way it works is at every moment in time, you throw away the middle third of every segment that's left. And you keep doing this until time is exhausted. So I throw away the middle third, and I'm left with the interval 0 to 1/3, and then 2/3 to 1. What's the length here of the initial segment? 1. What's the length here? 1.
2/3. Oh,
2/3.
both, okay.
Right, because you're both. Yeah, it's unclear what I was asking. If you think about it, if we throw away 1/3, then we keep 2/3. In the next segment, we have 0 to 1/9, and then we'll have 2/9 to 1/3, and then we'll have 2/3 to, that's going to be 6/9 to 7/9, and then we'll have 8/9 to 1. What's the length of the intervals here?
1/9.
Each one is 1/9. What's my total length?
4/9.
4/9. Or 2/3 squared. Every time we go down another level, we keep 2/3 of what we have. So as time passes, what will be the length in the limit? What will the length go down to?
0.
The length goes down to 0. I don't have time to go down to infinity, but it seems plausible. Do any points survive, or is every point thrown away in the end? Do any points survive? Yes?
Would 0 and 1 survive?
0 and 1 will always survive. 0 will always start an interval over here. 1 will always end an interval there. What about 1/3? Will 1/3 always survive? Yeah. What about 1/9? Once you're an endpoint, you always survive. So if you think about it, and again, what I want to do right now is I want to try to excite some of you to mathematics. And I want to review some math that you should have seen in high school but may not have remembered. All the numbers that survive can be written in base 3 with no 1s in their base 3 expansion. So if you look at all the numbers from 0 to 1/3, they would all have a 0 if you're writing them in ternary. All the numbers from 1/3 to 2/3 would have a 1 because they would have 1/3. And all the numbers from 2/3 to 1 would have a 2 as their first digit expansion. So everybody's familiar with base 10. We like base 10 because we have 10 fingers. Computers like base 2 because on and off. You can do things in base 3. And so it turns out that the numbers that live, so you survive, if and only if you have no 1 in your base 3 expansion. Why don't I just say your decimal expansion? Decimal means 10. The decimal expansion is what you come when you use 10. You'd have 1/10, 1/100th, 1,000. Here we have 1/3, 1/9, 1/27. So the only numbers that survive are the numbers that don't have a 1 in their base 3 expansion. How many such numbers are there? Well, if you give me any number that has no 1s in its base 3 expansion, what are the only numbers it has? What will be the only numbers in its base 3 expansion? Zeros and 2s. So all you need to do is take any expansion. So let's say we can write x as x0, x1, x2, x3, dot, 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 dot. And that means x is equal to I guess I'll just write it this way, as x1 over 3 plus x2 over 3 squared plus x3 over 3 cubed plus dot, 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 dot. What I can do now, and I'm going to do this fast and informally, is look at the new number y, which is x1 over 2 over 2 plus x2 over 2 over 2 squared plus x3 over 2 over 2 cubed. So when you think about that, all of my numbers on top are going to just be zeros and ones. This would be the base 2 expansion of a number. So there's essentially a one-to-one correspondence between base 2 expansions of numbers and the numbers in this set. Well, every number has a base 2 expansion. What this is telling us is that the number of numbers in this set is the same level as the total number of numbers in the interval 0, 1. It's the same infinity as that set. So I'm not going to go into too much detail right now. You can calculate the dimension. It's the log of 2 base 3. Let's see if I'm doing this correctly. Yes. What kind of, roughly how big is a log of 2 base 3? What can you tell me about that number? Is it positive? Is it negative? Is it large? Is it small? You want to have some sense of what a number is. If I didn't have the log of 2 base 3, if I had the log of 3 base 3, what would be the log of 3 base 3? 1. So is this larger or smaller than 1?
A little bit smaller.
A little bit smaller. Good, so its dimension is less than 1. That kind of makes sense because it's not the whole line. What's the log of 1 base 3?
0.
0. So this is larger than 0. So its dimension is somewhere between 0 and 1. And later in the semester, if people are interested, I'll show you why that's the dimension. All right. What I want to do now is I want to talk a little bit about binomial coefficients. How many of you have not seen binomial coefficients before? Okay. So it's not a prereq for the class. It is helpful to have seen them. The other reason I wanted to do this was just to start talking about series. And I'll just actually write some notation right now. I might write y is the sum and goes from 1 to infinity of xn over 2 to the n. As just a nice way of codifying what I mean by this. You know, a nice compact notation. Yes?
Why don't you write 2 to the n plus 1?
I could do that because I really want to view this as this is being divided by 2.
Okay.
Is that the 2 is really supposed to that because the xn's here are either 0 or 2. And it's because of that this will always be an integer. And that's why this is going to be the binary expansion. Okay, so I want to just quickly review binomial coefficients. You should have seen them in calculus. The other reason for doing this is the end of the second week. I know the first week was not a real week of class, we had one day. It's wrong to go too far in this course without doing some calculus. So I want to basically show you that with high probability, almost all of you have mislearned calculus from your teachers. All right, so binomial coefficients. N factorial is the number of ways to arrange n people when order matters. Is there a difference between being president and vice president? Yes. Is there a difference between being the representative of one building on college council versus another building? No. For something like that, a lot of times representatives are all equal, but offices are different. So n factorial is n times n minus 1 times 3 times 2 times 1. So if you think about it, if I have n people, I have n choices for who's first. Then that leaves me n minus 1 people left over for the second slot, and then n minus 2 for the third slot. What should 0 factorial be? How many ways are there to arrange 0 people when order matters? One. There's one way to do nothing. You can't do nothing many different ways, then you're doing something. It's just a good definition. Later in the semester, people are really interested. I will actually show you that the number of ways to arrange negative half of a person is the square root of pi. You want to talk about strange formulas in mathematics. There is a way to interpret arranging negative half of a person. Okay. Now, imagine you have k people from n, and order matters. Then you have n choices for the first, n minus 1 for the second, all the way down to n minus k minus 1 for the last. That will be the number of ways to choose k people from n when order matters. Okay? If the order doesn't matter, then you divide by k factorial. And the simplest way to see that is, this is the number of ways I can choose k people from n when order doesn't matter. But if I have k people, how many ways are there to arrange those k people? K factorial. So imagine I have 4 ghosts. Anybody know the names of the 4 ghosts? Yes?
Inky,
Yes?
Blinky,
Yes?
Pinky, and Clyde.
Very good. Email me for cultural extra credit. Those are the 4 Pac-Man ghosts. There would be 4 factorial or 24 ways of rearranging them. So over here, if I chose 4 ghosts from the set of n, and they might also include maybe Casper and maybe the ghost from the movie Ghost, I would have Inky, Blinky, Stinky, is it Stinky? Pinky, Inky, Blinky, Pinky, and Clyde. They would count 24 times. In 6 of the times, Clyde would be first. In 6 of the times, Clyde would be last. So if order doesn't matter, then we have to divide by k factorial. One of the most important things in mathematics is to learn how to do nothing. We really have 2 ways of doing nothing. We can add 0, and we can multiply by 1. And then one of my favorite professors at Yale, Peter Jones, paused one day and says, the log of 1 is 0. There's really only one way to do nothing. What I want to do here is I want to do nothing. The bottom looks like a really nice factorial. It's got k factorial. Look at the top. The top is screaming at you to do something to it. What does the top want? What does it want to be? What does the top want to be? It wants to be a factorial. Which factorial does it want to be?
N factorial.
It wants to be n factorial. But it's chopped off. So what do we need to make the top n factorial?
N factorial minus k factorial.
N minus k factorial.
Oh, yeah.
So if we multiply now by n minus k factorial, now the top is just n factorial. Are you allowed to just multiply the top? No, this is like the 13th, 14th, 15th Amendments of the Constitution. We must treat all parts of equations equally. If I do something to the top, I must do the exact same to the bottom. So I will divide by n minus k factorial. Now I've just multiplied by 1. What I hope you start to notice as the semester progresses is how much of our life is spent doing algebra. This is not a class that you just want to ignore from high school. You really want to get comfortable with finding ways to look at the expression and see what's going on. Now we get the nice formula n factorial over k factorial n minus k factorial. And you might remember this from high school written as n choose k. Or sometimes they write it as nck on your old calculators. This is the number of ways of choosing k people from n when order matters. What this immediately tells you is the following beautiful theorem. It's also the number of ways of excluding n minus k people. If you choose k people for something special, that's the same as choosing n minus k people not to get the something special. And so you could prove this algebraically, that n choose n minus k is the same as n choose k, but you can also prove it by story. There's a lot of beautiful stories we could do here. When I teach probability, I actually spend about a week doing a lot of these probability stories. There's a nice one in terms of how bad Amherst is. All right. So I want to get to the applications of this to calculus. So x plus y to the n is x to the n plus n, x to the n minus 1, y plus plus y to the n. It has some expansion. It turns out it's the sum, k goes from 0 to n choose k, x to the k, y to the n minus k. Or you could also write it as the sum, k goes from 0 to n choose k, x to the n minus k, y to the k. How many of you have seen this? This is the binomial theorem. How many of you have seen this?
A little bit.
A little bit, okay. We may have a longer lecture on this when we have a little bit more time. It's such a beautiful, wonderful result. Related to this is Pascal's triangle. One. I'm just writing the expansions. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on and so on and so on. And these numbers here are coming from the expansions here. So if I take n equals 3, that would be this row over here. How many of you have not seen Pascal's triangle? Okay. So every number is the sum of the two ones above it, and you have all ones on the outside. The reason we need this in a calculus class is we want to find derivatives of functions. So for instance, how does this come up in calculus? Well, let's say we want to calculate the derivative of x to the n. It's going to be the limit as h goes to 0 of x plus h to the n minus x to the n over h. And so if you really want to do this, we have to understand what do we get when we expand x plus h to the n. The binomial theorem tells us what we get. We will get x plus h to the n is the sum, k goes from 0 to n choose k, x to the n minus k, h to the k. So the first term is the k equals 0 term, so we'll just get x to the n. The next term will be n, x to the n minus 1h. the next term will be n choose 2, x to the n minus 2, h squared. So everything from here is h squared or higher. H cubed, h to the 4th, h to the 5th, h to the 6th. So when I subtract x to the n, this cancels. When I divide by h, the h here is gone, and then everything else here will still have an h. And then when I take the limit as h goes to 0, none of these will contribute, and that's where the nx to the n minus 1 comes from. I actually don't need the full strength of the binomial coefficient. I don't need to know that this is n choose 2. I just need to know the expansion looks something like this. Well, essentially, it's a no shit moment. I'm expanding out x plus h to the n. The only things I can get is I have some number of x's, I have some number of h's. And if you think about what's going on, I have n factors, x plus h, all the way down to x plus h. For each factor, I choose either an x or an h. How many ways can I choose x 5 times? And choose 5. And that will give me the term x to the 5th, h to the n minus 5. This is what we need to do to calculate the derivative of x to the n. So what I want you to think about is how do you take the derivative of x to the r? We've only done this when n is an integer. How many of you can tell me what the derivative of x to the square root of 2 is? Derivative of x to the root 2, what is it? You should have learned this in calculus. What's the derivative of x to the...
It's going to be the square root of 2 minus 1 times... No, wait. Oh. No, the square root of 2 x to the square root of 2 minus 1.
Great. What the hell does it mean to take a number to the root 2th power? Or I don't know, but that's what the answer will be. So your answer is correct. But think about, what does it mean to raise something to the root 2 power? You have the right answer. So, and then the question is, how did you prove what that was in calculus? Or did your teacher somehow get something by you? When we prove the derivative of x to the n, we are using the binomial thing. We're expanding things out. How do you get x to the 3/5? You can modify this and get x to the 3/5. It's a little hard, but you can. All right, so I want to end with a wow moment. We have a perspective here. We've got to show them what we do at Williams. You've all looked at Pascal's Triangle before? We're going to play a game. If the number is odd, we'll color it in as a circle, and if it's even, we'll delete it. We don't like even numbers today. Okay? And then the question is, as Pascal's Triangle gets bigger and bigger and bigger, what kind of shape will you get? Now, I wrote a computer program to do this because I couldn't find anyone on the web to have done this. The way my program works, it was a little bit easier if rather than having the vertex over here and coming down, I had the vertex here and going outward like this. I don't really feel like rotating the projector, so just do it like that. Now the other thing is, as the triangle gets bigger and bigger and bigger, that's more and more rows to see. It's going to be harder and harder to view this. So what I've decided to do is if it's displaying 1,000 rows or 5 rows, I'm always going to rescale things so it's always inside a unit square. Okay? So I'm just constantly just rescaling things so it always stays in the same size. So I'm not sure how well this will look on the screen because I'm not using the high-level recording. All right, so are we ready for the movie? This will probably not work for the people watching at home. Oh, wait. And it's not working for you either, so. All right, let me try that again. Is it showing up now?
Yes.
Okay. Ready? 1, 2, 3, go. So it's slowly adding points. When you can begin to see a shape, let me know. So it's basically adding like one row at a time. Is some structure beginning to emerge?
Yep.
Yeah. This looks very fractal-like. It's the Sierpinski triangle. Essentially what you do is start off with an equilateral triangle, break it into 4 small equilateral triangles and throw away the middle. And then for each one of the equilateral triangles that remains, break it into 4 and throw away the middle. And so you can see the structure emerging. Now I'm going to speed it up a little bit because class is about to end. And you can see more and more rows of Pascal's triangle. So the point is to just show you that the math you've been seeing since high school and earlier, there's a lot lurking underneath that you may not have seen. Okay, and it looks like, yes, that is not recorded at all. It is a blank screen for those at home. Okay, all right, good place to start.